Hello everyone. Welcome to ENPM 808A ENAI 600 titled Probability and Statistics for Engineering AI. As we all know, artificial intelligence is gaining a lot of momentum and will be a dominating field over the next several years. As the phrase artificial intelligence indicates, it's a paradigm where decisions are made not by humans using human intelligence, but instead made by machines. The question is, how likely is that decision made by a machine the correct decision? The moment we use the phrase how likely, we inevitably enter into the world of probability theory, which is what we will learn in this class. This slide provides you a course outline, a set of topics that we're going to discuss during the semester. We start off with Introduction to Probability Theory, where we lay the foundation for probability theory via an axiomatic definition of the probability metric. Once we are comfortable with that, we move on to what is known as conditional probability and Bayes' rule. Now, this is a very relevant topic for artificial intelligence. You all must have seen AI in action with the autofill feature that you all have come across in various messaging platforms. For example, if you open up your phone and try to send an SMS, and let us say that you type the word my, then an artificial intelligence algorithm may give you a few choices as to what the possible next word you may type be. It may give the words like mom, dad, favorite, etc. So what's happening is the AI algorithm is picking those three words as the three most likely words that you could have possibly typed, conditioned upon the first word being my. So there is a conditional probability that the algorithm computes as to what is the most likely set of next words, and that's what it gives you as options. Now, the Bayes rule is related to conditional probability in the following sense. Let us say, as an example, we all know that if you have COVID, you have a very high likelihood of fever. But if you have fever, what are the chances that it is COVID? The medical doctors always come across these situations, right? A patient comes with a symptom. The question is, what is the underlying disease that led to that symptoms? Because multiple underlying diseases can lead to the same symptom. So what's the likelihood that a particular disease could have caused this symptom to occur? So in probability theory world, we call this as computing posteriori probability, or it's essentially getting the probability of an event B given an event A if you know the probability of the event A given B. So it is that type of computations that we'll learn in this particular topic. Then we move on to the definition of a random variable. A random variable simply allows you to map events in probability space to real numbers. This way, the machines can do the number crunching for the random variables that takes on different probabilities. Once we are comfortable with the concept of a random variable, we move on to the definitions of probability density function, probability distribution function, and conditional density functions. We discussed some popular density functions, including the famous bell-shaped density function called as the Gaussian density function. You all would have come across that in one form or another. And so we'll go in depth into the Gaussian density function in this class. Once you're comfortable with probability density functions, so on and so forth. We deal with what is known as functions of random variables. I mean, as an example, let's say there's a factory that manufactures a circular disk, and let's say that nominally the radius of the disk is supposed to be 10 centimeters. But there's no guarantee that the disk that is produced is exactly 10 centimeters in radius. It could be, 10 centimeters plus or minus 0.5 centimeters. All of a sudden, the radius of this disk now becomes a random variable distributed between 9.5 centimeters and 10.5 centimeters. And now, if we know the density function of this radius of this disk, how can we compute the density function of the area of this circular disk? We all know that there's a relationship between the radius and the area. So knowing the density function of the radius, how can we compute the density function of the area? So those are the types of things that we learn in this topic. Then we move on to moments and moment generating functions. For example, in the example that I gave earlier on about manufacturing of a circular disk, and I said a nominal radius of 10 centimeters. That's essentially what I'm saying is the average radius of the disks produced by the factory is 10 centimeters. So that moment or the average is called as the first order moment of a random variable. But then it is not just sufficient to tell the average. You want to know what is the spread, or that is how much can it deviate from the average. That is called as a standard deviation. And there's a relationship between standard deviation and variance, which we'll also learn in this class. And then we'll also learn what we call as higher order moments of a random variable, because this is a very important topic when we deal with functions of random variables as well. Once you're comfortable with moments of random variable, we talk about conditional moments. Recall that we started off the semester with probability theory and then moved on to conditional probability. Similarly, here we talk about moments and then we go on to conditional moments. Again, I'll give you an example that helps you appreciate what this topic is about. Let's say somebody conducts a survey of the salary over a large population of engineers. Based on that data, if you're asked what's the most likely salary that one can expect for a person with electrical engineering and 10 years of experience, you should be able to answer such a question using conditional moments, which you're going to learn in this semester. Then we move on to another important topic called as parameter estimation. We all have heard that AI can mimic the voice of a person. Now, what does it do to achieve that? It uses a parametric estimation. In other words, it models a person's voice by a set of parameters that represents the vocal tract of that person. Now, how do we estimate these parameters is what we'll learn in this class. Then we move on to hypothesis testing, again, a very important topic in AI. We just said that AI can produce or reproduce a person's voice, right? The question is, how well does that AI algorithm produce somebody's voice? How does it compare to other AI algorithms? So what you do there is you test multiple AI algorithms over some limited set, because it's impossible for you to test over over the entire population as to whether this AI algorithm is able to reproduce every person's voice in this world. So you're limited by a sample of the total population. Knowing what you will evaluate on a subset or a sample of the overall population, what can you say about the overall performance of the AI algorithm over the entire population? How does it compare with some other AI algorithm? These are the types of things that we will learn in hypothesis testing. That is, with what level of confidence Can you accept or reject a given hypothesis? Finally, we move on to a very important topic again called stochastic processes and Markov chains. A stochastic process is simply a time-indexed random variable, which means at every instant of time, it is a different random variable. Now, there are many applications where the state of the system in the next instant of time is entirely dependent on the state of the system in the current instant of time and nothing from the past. Such systems are also called as memoryless systems because it has no memory of the past. Markov chain is a state diagram representation of such a system. A good example is a call center. Let us say right now there are 5 people waiting for their call to be answered. At the next time instant, there can be 6 people waiting for a call to be answered if one new user makes a call and no user has left the system. Or in the next instant of time, there could be 4 users waiting if one person exits the system after being served by the call center. Or there could be still 5 users if there is no new user that enters the system or a user that's already in the system doesn't exit. So everything depends on the current state of the system, which is 5, and what happens at the next instant of time. So you all, when you call a call center, you'll get a message telling the average call hold time is 20 minutes. Now, how does the machine come up with such a number? This is what we're going to learn in this semester. So these are the various topics very relevant to artificial intelligence that we're going to learn in this semester. So this next slide is only talking about, the textbook that we'll use for this semester. And, there'll be 2 exams, one midterm and one final. And there'll be homeworks assigned on an average every 2 weeks. So finally, when you complete the course, you will be able to understand the fundamentals of probability theory, statistics, and random processes, apply these concepts to the field of artificial intelligence and machine learning. That whole conditional probability is a way to decompose seemingly complex problems into solvable framework. And then you'll be able to analyze functions of single and multiple random variables. Again, as I said, we'll go in depth into the discussion of Gaussian random variables and its applicability to a wide variety of applications, including artificial intelligence. And then we'll learn about hypothesis testing to determine the most likely outcome and feed that information back to the machine learning framework. So I hope you'll enjoy the semester, and I look forward to seeing you all. Thank you very much.